Hello, hello. Can you hear me? Is my audio clear? Hello, hello. We'll wait for a few minutes for the participants to join and then we'll start. Good afternoon, everyone. I hope you are all fine, doing well. So today we'll be starting with thermodynamics. We'll be waiting for 1 or 2 minutes more. That's it. And then we'll be starting. Fine. So today we'll be talking about thermodynamics. Right? I've already heard about what is thermodynamics and all, and it is very much important for you. That is in case of JEE as well as NEET also. Both cases there will be questions. 1 to 2 questions are seen almost many times here. Minimum for a paper, 1 to 2 questions are there from thermodynamics for sure. Okay, so try to see what is going on here. No, just try to confirm whether my audio, video, and presentation all are clear or not. Okay, you can confirm in the chat. If you have any clarifications, try to mention it in the chat. Okay. If there is nothing like that, then we can continue. Firstly, today we'll be discussing about some introduction of thermodynamics, what is that and all, and some terminology, right? You already heard terms like enthalpy, entropy, these things. So we'll be seeing before going to terminology, we'll be seeing how these terms are defined actually. No, first thing is internal energy. Afterwards, we'll be seeing, and after internal energy, what is heat and what is work. And if time permits, we'll go to zeroth and first law of thermodynamics. Okay. First thing, thermodynamics. What does it deal with? It is a branch of science, right? We are talking about science itself. So which deals with the study of different forms of energy and quantitative relation between them. Try to understand. What are you seeing in this case? Can you see? Can you see what is there on the screen, right? What is there on the screen? What can you see? Something red color, right? What is that? Yeah, right. That is nothing but charcoal burning, right? It is showing a red kind of tint color. That is nothing but representing the heat produced from it. Why is this heat produced? Nothing but due to combustion of the carbon inside the coal. Nothing but what is happening here? Chemical energy, that is coal, is being converted into heat. It's a different type of energy. Right? Now, how to relate this chemical energy and heat energy? That relation and study of this energy conversion is nothing but thermodynamics. Clear, everyone? No. Does the chemical energy convert only to heat? No, right? It is also converting into different. For example, if we take a galvanic cell, right? We'll be taking two different beakers, and left side will be your anode and right side will be your cathode, right? So we'll be connecting it through a, let's say we are connecting it through a bulb. And there will be our salt bridge, right? If you remember. And we'll be filling it with its metal salt solutions, right? Aqueous metal salt solutions. Now, then what happens? Due to the transfer of electrons here, the bulb will start to glow. What is happening here? The chemical energy is being converted into electrical energy. Now, what is happening? We need to relate between, again, chemical energy, that is the spontaneity of a reaction, or let's say enthalpy of a reaction, and electrode potential of a reaction, right? Electrical energy, potential of a reaction. So this will be seeing in this case, okay? How we need to relate between two different types of energy. Right? Can energy be destroyed? No, it will be converted from one form to another form, right? The same thing. Now, first thing before going to how the energy is converted and how to relate them, firstly we'll be seeing how we'll be taking a particular item or thing as a system, or which one we'll be considering as surroundings. Now, in this slide, what are you seeing? What is the image you can see here, right? What are you seeing here? Nothing but a human, outline of a human. Nothing but, not totally human, right? It's an outline of the human. Now, let's say consider you are particularly seeing this particular human. Now that human, whatever we are seeing, it is called as our system. Okay, this is called as system. What we want to see is called as system. Now, whatever the other things surrounding the system is called as surroundings. Now, whatever present around this human outline is nothing but surroundings. Okay. Now, system is nothing but the human being. If I take consider you as a particle or you as the thing, you will be the system. If I consider me as the thing, I'll be the system. Clear. Now, whatever other than, if I'm considering you as the system, and other than you, whatever is there on the total universe, that is nothing but your surroundings, right? Clear. Nothing but whatever is covering around you, that is nothing but surroundings. Now, there is a difference between system and surroundings again, right? Where the system and surroundings will be differentiated. Now, the outline here you can see, this is called as border or boundary. This is nothing but the partition between the system and surroundings. The boundary is nothing but a small layer over the system. Now, in this case, what is our boundary? What is the human boundary? That's nothing but a skin, right? Now, whatever you consider, whatever system you consider, what is covering around it, that will be your boundary. What is the layer differentiating the system and surroundings? That is nothing but your boundary, and the particle or the thing you are considering, that will be your system, and the surroundings other than the part will be your surroundings. Clear, everyone? Now, let's say you are taking a bottle. Okay. Let's say you are taking a bottle. full of water. Now, if we consider this bottle as our system, nothing but whatever inside it is there, that will be our system, full of water. Now, the covering will be our boundary of the system, right? Boundary of the system. Will you find water out of the plastic layer? No, right? If it is broken, it can be seen, but if it is fine, everything is fine, that will be your boundary, right? Now, after this boundary, whatever it is there, the whole thing will come under surroundings. Clear, everyone? What is system, what is boundary, and what is surroundings? Now, you can note this. System is nothing but part of universe we are interested in, what we want to particularly see. That will be the system. Okay. In case of human being, what is the system? Whatever is present inside the skin, all the organs and everything comes under the system. Okay. If case of water bottle, we have seen the whole water will be coming under the system. Okay. The next, after seeing the system, what we need to see? The surroundings. Other than the system, everything is coming under surroundings. The rest of the universe is nothing but our surroundings. Part of the universe which we are interested in is the system. Apart from that part, everything will be our surroundings. Clear? What are you seeing here? If you want to represent the universe, what you will be doing? Universe is nothing but whatever the system we are considering plus the total surrounding will give you the universe, total universe. Clear, everyone? System and surroundings. Okay. If you add system and surroundings, you'll be saying the whole universe. We are representing the whole universe. The next thing. The next thing is boundary. What is boundary? Nothing but the differentiating layer between the system and surroundings. That is nothing but a boundary. Okay. Try to note on these. One thing is system, part of the universe we are interested in, and next thing is part of the universe, rest of the universe, that is nothing but our surroundings. Boundary, nothing but the layer differentiating between the system and surroundings. What is universe? Nothing but system plus surroundings is nothing but our universe. Okay. Now we know what is the system. Now we need to discuss what types of systems are possible based on what kind of energy transitions will happen, or what kind of transitions will be happening. Maybe matter, maybe energy, or anything else. Okay. Now, firstly, we'll be taking open system. What are you seeing here in this open system? Can you see anything here in the open system? Now, in the open system, we are seeing water in a beaker, right? Now, is the beaker closed? No, it is an open beaker. Okay. Now we'll be seeing water in an open beaker, and then we'll be heating the water beaker. Clear, everyone? The red color is showing the heating, and the blue color will be representing the water itself. Okay. Now what are we doing? We are heating the water. Initially, what happens? The water will be absorbing the heat, right? Initially, the water will be absorbing the heat. After absorbing the heat, what happens? The kinetic energy will increase, and the intermolecular attractions between the water molecule decreases. And afterwards, what happens? That will be directly the water molecules will break down and go into vapor form, into gaseous form, from liquid form to gaseous form whenever it reaches boiling point. Right. Now, after it is reaching its boiling point, it is undergoing vapor. The first thing, what are you observing in this total system? The system you are considering is the open vessel you are seeing, and which is consisting of water. This is your system. Now, if you are heating, nothing but you are giving energy from the surroundings to the system. The system is absorbing the energy, and then it is being converted into water vapor, from liquid phase to water vapor. Now, the gas doesn't stay there itself, right? So what happens? The water molecules, which are in form of water vapor, will be escaping from the system into the surroundings. It will be dispersed into the surroundings. Now, first thing, energy transfer is happening. Second thing, that is nothing but matter is also being exchanged from system and surroundings. Nothing but, see, if you take this one as this until here as our system, what is happening? Water vapor is coming from system to surroundings. Clear, everyone? What is happening here? The matter is escaping from from system to surroundings, as well as the energy is also being transferred from whatever heat we are producing into the water. Try to note down the definition. What is an open system? Nothing but system which can exchange both matter and energy with the surroundings. That is, it should be having exchange between nothing but it should have a possibility to exchange the thermal energy or any other type of heat energy, and also it should be able to exchange the matter from the system and surroundings. That will be coming under the first type of system, that is open system. I've given you one more example also here. That is nothing but if you take marble, what is marble made of? Nothing but CaCO3, right? Calcium carbonate. If you take calcium carbonate, nothing but a marble piece, and HCl liquid, and heat it, it will directly give us water. Sorry, it will give us carbon dioxide. It will give us carbon dioxide gas. In case of water, after heating, what happens? Water vapor was given. If you are taking marble and HCl, calcium carbonate and HCl, and if you heat it, it gives rise to carbon dioxide gas, where again matter is giving escaped and also thermal energy also being transferred. This is also one type of open system. Clear. Now I have seen open. What happens? Try to keep a lid on it. That will be our closed system. Clear. Now, how many of you know pressure cooker? I think you people know pressure cooker, right? Seen any time? Let's say before the whistle, we'll be considering the pressure cooker before the whistle itself. The whistle not going. Okay. Then what happens? Whenever we heat it, what happens? Pressure cooker, the water will boil inside and the vapors will form, and the vapors will again condense and come down. This will be happening, right? So here the water vapor is not escaping from the system towards the outside of the system. Here matter exchange will not be there, but what are you initially seeing? The heat we are transferring from the surroundings, that is outside, into the system to boil the water. This is nothing but heat transfer, but there is no matter transfer here. The matter is not escaping from outside, from inside the system towards outside the system. Okay. Now, if you see here in the system, the same thing again, the blue color with water. Okay. And this will be our water vapor. Okay. Blue is representing water and water vapor -1, and the red one will be representing the heat. Let's say we are giving the heat again. Now, due to the heat, what happens? Due to the heat, what happens? Again, water will be boiling and it will be converted to water vapor. Now, here, as the container is closed on the above surface, here the container is closed, it is not open. The system is not open here. As we are closing it completely, there is no possibility of the matter to escape from the system into the surrounding. The whole, whatever inside this orange one will be our system. Okay. This orange one will be our system. And whatever surrounding, this orange line will be our surrounding. Okay. Whatever surrounding around it will be the green one will be our surroundings. Okay. It will be our surroundings. Now, whatever you're doing, you are doing heat from the surroundings into the system, but the matter is not escaping from the system into the surroundings in this case. Okay. Now, try to note down system which can exchange energy with surroundings, but not matter. Clear, everyone? It cannot exchange matter, but it can exchange heat. Okay. Be clear with that. Okay. Now, do you have any real life example for this closed system? As I said before, the whistle, closed system, pressure cooker will work, no issues. Okay. There will be no exchange of matter in that case before the whistle. If your whistle is coming, that but the steam is escaped, right, to decrease the pressure. Why we need to decrease the pressure? If the pressure is going on building up inside the cooker, what happens? It will burst like a bomb. Okay. So that's why we'll be using whistle, so that the pressure will be maintained inside. Now, we'll be seeing third type of system, that is isolated system. First is open type of system. Nothing but what we need to see. The matter will be exchanged as well as the energy will be exchanged. Second thing is closed system, where only energy is exchanged but not matter. The third one, that is isolated system. We can make out the difference here. Right? Nothing but what you need to see is here neither heat can be exchanged nor matter can be exchanged. Whenever you take, let's say you are taking a thermally sealed vessel and you are pouring water inside and completely sealing it. Now, even if you are providing heat, the water cannot take the water the water cannot take the heat from the surroundings, nor the water can be boiled using that. Or as it is a closed container, again, we cannot see the escape or exchange of matter from inside the system to the outside the system. Now, if you see here, we are taking a closed vessel and this is our insulation. Okay, we are in a thick insulation so that the energy will not be transferred here. Even if you are providing heat here, if you are providing a fire also, due to this insulation, the heat transfer will not be happening. So what happens? There is no change in the water also, the intermolecular process, nor it will boil, anything will happen. So whatever initially was there, it will be the same. Now, as it is a closed container, it is a closed one again, there is no matter exchange, and due to insulation, there is no energy exchange. Energy exchange. Okay, simple, nothing but whenever you are taking insulator, right, you cannot heat it nor cool it because there is no energy transfer. And one more thing, when you are taking closed container, as there is nothing to escape, what happens? Whatever is there inside, whatever matter is there inside, the matter will be inside and it cannot come out. Only possible when the open surface is there, whenever there is escape process there. If there is no open end, nothing can go out. We'll be writing it as system which can neither exchange matter nor energy with the surroundings. Clear, everyone? These are nothing but isolated system. Try to note down the point. System which can neither exchange matter nor energy with the surroundings. Now, next we'll be seeing is isolated system. One example you will see seeing in the daily life. How many of you drink chai? Right. Many of you drink chai, right? So where will be storing this? In a thermos flask. Remember thermos flask? Now how it will be? There will be a plastic coating and inside there will be some insulation, and inside that there will be a glass thing, and inside that will be storing the tea or milk, hot tea, hot milk, or hot water also sometimes, right? These things will be done. So here these all will be acting as an insulator, and the water inside will be our system where there will be no exchange of matter. Why? We will be tightly closing the, see here we'll be tightly closing it with the cap. So because of that there will be no exchange of matter, and due to this insulation, this all insulation here, what happens? Due to insulation, what happens? Due to insulation, there will be no exchange of energy. Due to the closed system, there will be no exchange of matter. Clear, everyone? Try to understand these concepts. Okay. Next, we'll have a small concept test. Try to see the concept test and answer it. I think you can see the question, right? So it is which type of system? Now there is a diagram there. Now try to see that and analyze. It is which type of system? I'm giving you a minute. No. If you are fine with it, let's go. Yeah, right answer. Fine. Now, it is a what process? It is a isolated process. How are you saying that? In the diagram, what is given? Matter is there, and on the arrow mark there is a into. What does that represent? Nothing but matter is not being exchanged. Now, into on energy, that is also nothing but energy is also not exchanged. Where does this happen? Where is there is no energy exchange nor matter exchange? In an isolated process, right? The answer will be isolated process. Simple. Now, one more question for you. Let's say a tea is placed in thermos flask is an example of dash type of system, or can it actually act as a system? Try to go through the question. I'm giving you 30 seconds. A tea is placed in thermos flask is an example of open system, closed system, isolated system, or we cannot say that is a system actually. Yeah, you are right. It is isolated system, right? What is system? Nothing but whatever you want to consider that will be your system, right? Don't forget that. So here we are considering tea as the system, right? If tea is placed inside the thermos flask, it will be a isolated system where energy transfer doesn't happen, as well as matter transfer is also not happening. Clear, everyone? Now, let's see. First thing what we try to see what are the systems will be there before seeing the system. How do we see a system? Done with this, right? Now we'll be seeing what are the systems and how do we measure them actually. Now, state of a system, nothing but maybe gas or liquid or a solid. These things are nothing but state of a system, or whether it is in equilibrium or not in equilibrium. There are some states of system. Now, how do we say them? By seeing some type of parameters, nothing but measurable parameters of a system. Conditions of the system, which is described in terms of certain observable properties such as temperature, pressure, volume of a system. These are nothing but some measurable properties of a system. These are nothing but state variables. What is the state of the system and how we are measuring that is nothing but state variables. Clear, everyone? Now, we can measure the temperature, right, by using thermometer. How much height of the mercury is there? Nothing but based on that we'll be seeing the temperature, maybe in degree centigrade or maybe in Fahrenheit. Now, what is the absolute temperature? Nothing but in Kelvin scale we'll be calling it as absolute temperature. One more is if you're taking gas, we can see the pressure. If you're taking vapors, we'll be taking the pressure, right? We can also see the volume of the gases or liquids. Excuse me. This is nothing but state of the system and state variables. Clear, right? Nothing but what is the state of the system and how we are measuring it. That is nothing but our state variables. How many types of thermodynamic process do you see? We'll be seeing what is the system and then what is the process happening, what is the energy transfer is happening. And in that energy transfer, there are different types of process. It may be isothermal process, isobaric process, or isochoric process, or adiabatic process. There are 4 different types of thermodynamic process we'll be talking for now. Okay. Now, whenever we talk about isothermal process of a system is same thing again, whatever you want to see. Let's say we are taking the closed system and water is inside it. Now, isothermal process, nothing but we need to see that the temperature of the system should be constant. It shouldn't change. The temperature shouldn't change. That's the main thing. Okay. Let's say we are taking a bowl and inside there is a gas. There is a piston. Now, let's say T is equal to 30 degrees centigrade. Now, what I'm doing, I'm exerting some pressure, and what happens? The volume of the gas will be decreased. But here, the temperature we need to see, it should be same. The temperature shouldn't change. That's nothing but an isothermal process. And what is happening? Some work is being done here. So this work is not what work is done at a particular constant temperature. This will be called as isothermal process. Okay. We have different relations also, not only this one. Next thing is isobaric process. What we need to see here is the pressure should be constant. The pressure shouldn't change here. Okay. Here what happened? We are increasing the external pressure and the volume is being decreased. Now, in the next process, for a isobaric process, what we need to see is we need to keep the pressure constant here. Then, if the pressure is constant, we'll be calling it as isobaric process. Okay. Now, let's say what we are doing, we're taking the same gas and we are taking a piston above it. And now what I'm doing, I'm increasing the temperature from 30 to, let's say, from 30 degrees centigrade to 40 degrees centigrade. Now, what happens initially, if we are increasing the temperature, the collisions will increase. That means the pressure is increased. What we need to do, we need to keep the pressure constant. So So if you want to keep the pressure constant, what happens? The piston will go above so that the pressure will be remaining constant and the volume will be increasing here. Pressure will be constant and volume will be increasing to keep pressure constant. Okay, everyone, clear with this? Now, this is nothing but when pressure is constant, that is called as isobaric process, and this also is thing in states of matter also, right? You have seen what is isobaric, what is choric, right? The only new thing is adiabatic process. What is adiabatic process? Nothing but heat will not be changed. First we'll be seeing isochoric also. If volume is constant, the same thing in the previous reaction, what happens? If we don't rise the piston, the volume will be constant, the pressure will build up. That is nothing but isochoric process. At last we'll be seeing adiabatic process. Adiabatic process is nothing but there will be no heat exchange. Heat exchange will not be there. No heat exchange. Okay, that is called as adiabatic process. Here the temperature also will be same. It doesn't change. The heat of the system will not be changed. Heat will neither be absorbed by the system nor given out of the system. Clear, everyone? In adiabatic process, there will be no heat exchange. Now, this is some graphical representation of a thermodynamic process. If it is isobaric, I said, right, pressure will be constant. What is constant? Pressure is constant. Now, if it is a isochoric process, what is constant? Volume is constant. What is constant in isochoric process? Volume is constant. Clear? Now, in isothermal process, what is constant? Temperature is constant. In adiabatic, what is constant? Heat, Q. Nothing but heat is constant. Okay. The graph will be kind of looking like, we'll be seeing in detail how we can draw these graphs and all. Just, this will be our introduction class, right, for today. Now, if you understand what are these types of processes, try to answer the question. Try to read the question properly. Gaseous system is placed with pressure P1, volume V1 and temperature T1. It has undergone thermodynamic changes where temperature is remaining constant. Now, this is what type of process? Isobaric, isochoric, or isothermal or adiabatic process. Which type of process is this? Try to read the question properly, you'll get the answer itself. Take 30 seconds. Take 30 seconds. Okay, yeah, it's right. That is, it is isothermic process, isothermal process, right? Here already you mentioned that undergoes thermodynamic changes where temperature is remaining constant. What I say, whenever temperature is constant, nothing but it is called as isothermal, same thermal process, temperature process. Okay, the answer will be isothermal process. Note on the question and answer. Now, we'll be seeing two types of properties. One is extensive property and one is intensive property. Here, what is the main thing you need to remember is extensive property is nothing but you need to see whether the property is depending on a particular amount of matter or not. If you are changing the amount of matter, if the property is changing, let's say we are taking weight of a compound. If you are taking 10 grams of compound and adding more 10 grams, nothing but the amount of matter is increasing there, as well as the property we are measuring, that is weight of the compound, is also increasing, right? Yes or no? That is nothing but if you are seeing weight 10 grams of Na, let's say, nothing but weight of the compound. Now adding more 10 grams, that means matter is changing. Totally weight of the compound final will be equal to 20 grams of Na, right? Yes or no? Now, when we come to intensive property, this is independent of the amount of matter you are taking. Now, do you remember anything? What number of moles do you remember? Number of moles is nothing but weight by molecular weight. Now, whenever you take 10 grams of sodium or 20 grams of sodium, the molecular weight of sodium will be same, that is 23 grams, right? Yes or no? Molecular mass or molecular weight of sodium will be Same, that will be 23 grams irrespective of how much amount of matter you are taking. Clear? If the property is depending on the matter, amount of matter, that is extensive property. If the property is independent of matter, that is nothing but an intensive property. I for independent. Remember it in that way. Don't get confused here. Okay. Intensive for I, independent for I. Okay. Depending upon the quality of this matter contained in the system, that is nothing but an extensive property, independent of amount of the systems present in the system, amount of the substance present in the system, that is nothing but amount of matter present in the systems. If it is a system, if it is independent, that is intensive property. Try to note on the points as we go through. Depend upon the quality of the matter contained in the system, as well as it is additive process. What we did, 10 grams plus 10 grams, we added that, right? No, intensive property, can we add like that? No. Do you add molecular weight? If you are taking 10 grams, the molecular weight of sodium is 23. If you are taking 20 grams, the molecular weight of sodium is 23. Same, but you will be adding, if you are taking 10 grams and adding 10 grams, you will be adding the molecular weight 23 plus 23. No, we will not be adding in such way. Okay. Whereas extensive properties are additive in nature, but intensive properties are not additive in nature. Ratio of two extensive properties is an intensive property. Right? If you take a ratio of an extensive property, you get an intensive property. No. Some more nothing examples here, nothing but examples of extensive property: mass, volume, heat capacity, these things. Now, what is the examples of intensive property? Molar mass, molar volume, molar heat capacity, specific heat capacity, these things. Nothing but how much heat is required to improve or increase 1 degree centigrade of a particular substance. That is what heat, specific heat capacity. Okay. Now, if you are clear, if you have any doubts, try to ask it in the chat. Until now, what we discussed until now, nothing but what is system, what is surrounding, and how many types of systems are there, and what are the thermodynamic process and types of properties, extensive property and intensive property. If you have no doubts, then let's see a concept test quickly. Here, the question is there. Try to go through it and answer. I'll be giving you exactly 30 seconds. Yeah, you are right. The option is option C. What did you say that? Nothing but entropy. C. Entropy is an extensive property. How you can say that? As we increase the number of moles in a container, the collisions will increase, as well as the entropy will increase. That is not one extensive property, depending on how much amount of matter is present inside a system. Now, if you take 10 grams of sodium or let's say 1 liter of water or 2 liters of water, both will be having same boiling point itself, right? The temperature is changing there? No. Clear, everyone? Try to see that. Whether you are taking whatever it is, the temperature will be an intensive property, and it is not depending on how much amount of matter you are taking, whether 1 liter of water or 2 liters of water. But the entropy will be changing. If you are taking 1 mole of gas or 2 mole of gas, based on that, the entropy will definitely change. Now, this is one more concept which we are going to see, that is state function and path function. Simple things to remember here, nothing more. State function, what we'll be seeing is that here will not be more seeing whatever path we are choosing. Only we'll be seeing is the first state and final state, nothing. Now, let's say there is a, your home is here, okay? Your home is here. This is your home. Now, what we need to do, we need to go to buy vegetables here, okay? We are going to buy some vegetables, okay? I'm drawing leaves, okay? Fine. So let's say you are there and your brother is there, okay? You and your brother. So you are going through a long distance so that you love the walk along the fields, okay? So you are going to, in this way, the long way. Initial position and final position. This is your final position. Now, same thing, your brother is taking shortcut direct route. Now, In state function, what we'll be seeing is directly initial position and final position. We'll not be seeing whether you are going through a long path or short path. Okay, whether you are long path or short path, no issues. What we will be seeing only thing is whether you are reaching the final point or not. What is the initial point? What is the final point? You'll not be seeing what path you are choosing here. Okay, that is nothing but a state function. If the value of physical quantity depends only upon the state of the system and does not depend on the path by which the state has been attained. Now I can give you one more example here. Right. If let's say we are going have a building here. Okay, there is a building and there is a lift also here. Okay, now what are you doing? You are going and climbing the lift and you are going to the above floor here. Okay, in lift you are going, or one thing is there, you can go through the stairs. No, if you are taking stairs or if you are taking lift, the final position is on the 5th floor itself, right? It is not changing. So here what we need to see, let's see the property called potential energy. If we see the potential energy, what is happening? The initial state is on the ground and the final state is on the floor, highest floor. In this case, that is nothing but 1, 2, 3, 4, 5th floor. Okay, 5th floor. What is happening? The potential energy is increasing. As the height is increasing, the potential energy is increasing. Now here you will not be saying whether you are taking stairs or whether you are taking lift. Both will be having the same potential energy because height from the ground is same in both the cases. Clear, everyone? No, the path function is different here. Path function will not depend on the path function will depend on what path you are taking. Okay, it is not like whichever path you take, the energy or whatever property we are measuring will be same here. So depending on whether you are taking the longest route to the shop or shortest route to the shop, based on that the energy will be differing, or whatever the property you are measuring will be different. Now, for example, let's say again we'll be considering the apartment itself. Now the lift is there, you are going again, you are climbing the lift, okay, and you are going to the top floor. Here you are there, and one thing you are going is through steps. Now in this case, in which case you will be doing more work? Going through the lift you will be giving more energy, or going through the stairs you will be giving more energy? Try to answer in the chat. Yeah, going through steps will be having required more energy, right? Nothing but what we'll be seeing, if you see the work done here, the work done by going through the lift is nothing. How much energy you are spending, that's better. If you see how much energy you are spending through the lift is less when compared with how much energy you are spending on the stairs, right? Now this is nothing but path function. Which path you are choosing, based on that the amount of energy you are spending is different here. But in case of potential energy, whether you take stairs or whether you take the lift, the height depends here. So the potential energy also will be same in both the cases if initial and final state is same. Okay, try to note on the example. Heat, work, heat capacities, these will be coming under path functions. Try to note down the examples. Quantities which are dependent on path or way the system has achieved a particular state, from the initial state to the final state, how they are achieved. If it is depending on the path, whether it is short or long, that is nothing but path function. State function, no, doesn't depend on the path, doesn't depend on path. If you take a path function, depends on path. Okay, if you, whenever you try to see or any property, try to think if you are changing the process, or you're taking different type of amounts, or if you're taking a long process or less small process, whether it is changing the property or not. If it is changing, that will be a path function. If it is not changing, that will be a state function. Now next new term, that is internal energy. I think you heard about this, right? Nothing but how much kinetic energy is in there, in you, or what type of rotational energy is there, or what type of potential is there, in all these type of whatever energy is present inside you, that will be called as internal energy. Internal energy of a system is nothing but sum of all types of energy associated with atoms as well as molecules. Let's say in solids, what happens? The molecules will vibrate. In gases, they'll rotate among themselves, they'll collide with the other molecules. So due to this velocity, there will be kinetic energy, there will be change in momentums, many things will come under. So here internal energy is nothing but U is equal to U, or we'll also call it as capital E also. Kinetic energy, if it is possessing, right? If it has potential energy, that is also there. It is rotating, the rotational energy will come. So there is a nuclear interaction, so there will be nuclear energy. So we will be adding, going on adding as the internal energies are more, many of them are there in a particular system. So what we'll be doing is we'll try to calculate the internal energy by taking two different points, that is final and initial points, so that we'll be calculating difference in the internal energy, as we cannot calculate the absolute internal energy here. We'll not be calculating absolute internal energy. Instead, we'll be calculating difference in the energy. Change in internal energy will be calculated. Okay. Change in internal energy will be calculated, not the absolute absolute internal energy. No, change in internal energy is nothing but U final. What is the final internal energy of the system? Minus what is the initial internal energy of the system. We're using this simple formula to calculate what is the change in internal energy of a particular system. We'll not be calculating the absolute internal energy of a system. Okay, don't forget this point. No. How do we derive all this? Just consider for a system. If you take internal energy, it is nothing but a function of temperature and volume. If you are changing the volume, that means the collisions will be differing again, because that the volume will be changing. If you are increasing the volume, if you are decreasing the pressure, what happens? The volume will be changing. And if you are increasing the temperature, what happens? The collisions will increase. That means the kinetic energy of the molecule is increasing, as well as internal energy of the molecule is also increasing. Right? Now, nothing but we'll be taking internal energy as a function of temperature and volume. Okay. We'll be ending with this small thing. We'll be writing it as nothing but du. If you write it in this way, du is equal to, at constant volume, du by dt, differentiate with respect to temperature. At constant volume, that will be du by dt into dt, plus at constant temperature, du by dv. At constant temperature is dv. Now what is I'm doing? At constant volume, nothing but this is a isochoric process, and at constant temperature is nothing but a isothermal process. Now if I'm keeping temperature of the molecule constant, nothing but what I'm doing, the kinetic energy, whatever internal energy is constant in here. Yes. Now at internal isothermal process, du will be equal to 0. That means this whole term will be equal to 0. Okay, this whole term will be equal to 0. Don't forget. So if we remove that term, that will be equal to du by dt at constant volume into dt. This is nothing but isothermal process. If an isothermal process is given, so there will be no change in the internal energy itself. Now this, if you want to write, you can write a change in internal energy is equal to integration of Cv dt. Cv is nothing but change in specific heat at constant volume. Clear, everyone? Now here what we need to understand is internal energy is internal. Note on this point. Internal energy is stored in molecular motion. If molecular motion is not changing, that means internal energy is not changing. Where we have seen in case of isothermal modes, where the internal energy did not change, so the molecular motion did not change, and internal energy was change in internal energy was 0. And the capacity depends, new point, capacity to change this depends on degree of freedom. Degree of freedom. Okay. Degree of freedom of the molecule. We'll be seeing what is degree of freedom of the molecules in the next section. Have a good day. If you have any doubts, you can clarify. If you don't have any doubts, you can you can exit the section.